Do you want to introduce yourself and the paper?
My name is Loren Rieth, and this is a paper about improving the long-term performance of the Utah Slanted Array in the peripheral nerve.
Okay. Cool. And how would you describe it?
For medical research. Okay. And this project is also done in coordination with the University of Utah on the DARPA haptics program.
Okay. And so can you go through it? Do you want to step through it?
The overall plan of the device is to have implants into peripheral nerves and muscles to control a bionic hand that has sensory that can evoke sensory percepts, both cutaneous and proprioceptive. My part of the project is to make the Utah Slant Array that can be in peripheral nerves for a year and stimulate nerve signals and evoke percepts. So to do that, some of the changes that we've had to do is we had a device. Originally, it was this connector, a lead that had straight wires, and then Utah Array on the end of it. And some of what we're going to talk about here is making this lead a helical lead and adding in these suture wings and this extra spacer there, and how that's improved the lifetime of the devices by quite a lot in the peripheral nerve applications. And then another part of the story is about the tip metallization, how that ages in vivo, and if that damage is related to the amount of charge that's injected versus the amount of indwelling time, and trying to do some statistical analysis to distinguish between those two. So starting with the lead story, I'll go ahead and come over here. We have the median threshold data and also the impedance data from HS2. So this is the first generation of helical lead. We've had two generations of helical leads. So HS2 had generation 1, HS3 had generation 2. And what you see is if you look at the impedances, they kind of start bluish and then they get maybe a little bit higher, but you start to see a lot of black holes in there, and that's where the wires broke. And so what I was able to figure out is, this is the first time I saw the actual open circuits where they have 2 megohm impedances where the wires broke. And I figured out with this bimodal population of impedances that meant that the wires were breaking outside the body. And so what I did is then I extended the helical lead all the way up to the connector, and I added a spacer on it so that the whole lead was helical except for this one little bit there. The first generation had a bit of straight lead outside the body, and I found that was where the wires were breaking. Okay, so we made that change, and then in HS2, if you look at the impedance data here, you can see it all stays blue. We still have some black boxes, which are where the wires are broken. So here we started with 6 broken channels before implant, 40 after implant, and it goes up to 25. So we lost an additional maybe 20 compared to here, including a lot during the surgery. Here, 7 to 7, and then up to 11, that's 4, and here 7 to 14, back down to 7, and these all track 1 for 1 for those, so none. So this is already a big improvement to HS1, HS2, and this was a very large improvement to the HS1, which is the straight lead subject. Okay.
Yeah, I mean this is it basically goes from like 10 or something like this. In HS2 has 40 and 80 and stuff like this set of broken leads, and then at this one, so it's at least twice as good, right? But what happened here? It goes from 12 to 11, so one unbroke itself.
Yeah, no, you can see in a lot of cases here you had 14 to 8, and so there is some stuff that happens in kind of the peri-surgical, and honestly, these connectors, and sometimes there's misregistration, and so I see sometimes some squirrely behavior. I'll be quite honest, and I don't understand all of what it is. I try not to get too caught up into like individual changes.
Don't think about it too much.
But it is, but that is why I went and checked and said, okay, do these correspond 1-to-1? And so it is nice to see when those are preserved over time. And in this case, they were relatively preserved, honestly. If you look at it, even here, to there, so you can see, fairly well preserved. And that makes me feel more confident, but I still take everything with a grain of salt.
So when is this technology going to be used for phone chargers?
Probably already is somewhere. Those really special ones that have like the braided stuff. I'm not sure. Yeah,
those are always fraying.
Down here, I've done formal bend testing, so 470,000 cycles. I won't go into why. Straight lead, 100% failure by less than 30,000 cycles. With the helical lead, we had some failure. All those failures were the platinum wires, not the gold wires. I had no gold wires of an N of 6 leads, each one having 64 channels. So only no gold wires broke, only platinum wires broke, and I think I can solve that by using multi-filler platinum wire. We also did a stretch yield test, elongation test of 15% strain. No single material can handle 15% strain in a linear fashion, so these all broke on cycle 1. We knew that was going to happen. That's just a materials phenomenon. But with the helical leads, we had no wire failure, either platinum or gold, after 470,000 cycles of 15% displacement. So the leads, very, very strong. The tip metallization, I went through and SEM imaged every single electrode from HS1 arrays and the HS2 arrays. And then I scored them on a scale of 1 to 4 to facilitate a statistical analysis. And so what you see here is the population of these. So you have a number of 1s, a number of 2s, 3s, and 4s. Some of them were severely damaged during X-Planet, so I sort of censored out that population. We had a median of 2 and an average of 2.1 to 2.0. And so if you compare that to here, the median was still 2, but the average went up to 2.5 to 2.4. And so we had a little bit worse scores for a longer indwelling period, but also had more charge injected. So which one is causing the increased level of damage? And I need to do the statistics to make sure that's a statistically significant difference between those two. So we did another statistical analysis correlating the level of charge injection. These were up to 16 millicoulombs. This was up to 1.4 millicoulombs. Is there a relationship between this and the amount of damage? And the answer is, in a preliminary statistical analysis that we need to re-verify because some of these numbers have changed, the answer was no, pretty definitive no. I did it to get a little bit better sensitivity. I binned out the really high charge injection cases versus the low charge injection cases and said, okay, for the high versus the low, kind of a simpler, maybe more sensitive test, was there a correlation to the level of damage? The answer was still no. And so what this means to me is that the main driver for this damage is the indwelling time, and I believe that's because the silicon is dissolving underneath the iridium oxide, leaving it susceptible to damage, and that's what's resulting in what we see here. So if I can get the iridium oxide to be a really conformal and protective layer and better protect the silicon, then that will increase the lifetime of the devices.
Okay, very cool. Cool, so what are some next steps?
So the next steps are, I'm in the process with BlackRock of doing technology translation. So we've learned quite a lot about a lot of these failure modes. So I'm trying to do, they're making some devices, I'm making devices, and we're trying to look at these and careful and start to translate our metallization process to them, and also do any last minute improvements we can before we make the final wireless devices for the human subjects.
Okay, cool. Is there anything that I didn't ask that I should ask?
No, you asked everything. You're a perfect interviewer.
I know.
Awesome.
Thank you.